A neutron is that thing inside the nucleus at the center there of an atom that has no charge. Is it no charge? I think it's no charge. I believe it's no charge. Isn't it no charge? It is no charge. Ne? So yeah, that thing inside, and then then we spoke about molecules and how molecules would be comprised of different atoms. So if we have an atom, we'll have a hydrogen atom which is smaller in size and mass than oxygen. Therefore, even when you see it, it looks like that, if you could visualize it. And then the atom is also said to have isotopes, and that's when we have different number of neutrons. So if we have maybe more or less neutrons, then the nucleus, the atom is said to be an isotope of the original atom. We did an example, chlorine, where 75% of the chlorine is normal chlorine and 25% is isotope, and we worked out the average atomic mass unit of chlorine. Then Rablela Anyan, we talked a little about chemical equilibrium, or rather atoms and molecules in the context of reactions, right? So an atom is, like, we can always ask ourselves a few questions about it, like where is it on the periodic table, which molecules are made up of which atoms, and how are they bonded. So in other words, okay, let me start with this slide. So this would be atom, that would be atom, and this would also be an atom. This, we could sort of think about this one as that atom, or rather as this atom. Ne? And isotopes, it's there. So then in this one, so here it's using percentage of isotopes to get the relative atomic mass. All right, and then here we are talking about, in this slide, we were talking about things to keep in mind when solving chemistry problems, ne? So the nice thing about this is that when solving these chemistry problems, there are reversible reactions, ne? Reversible reactions. I already solved, ne? The ones which showing in class, the ones that we asked in class, there are not a very large number of them, because a lot of the reactions that happen in nature are not reversible, and I think we talked a little bit about that. But in any case, before we even get to understanding a reaction, we need to first understand what are the atoms in the reaction, right? So which types of atoms are in the reaction? And then secondly, we need to look at how these atoms form the molecules and how these molecules interact with each other. Ne? And then lastly, we work out the reaction where we balance the reactants, which are the things that react, and the products, which are things formed after an reaction. Things formed after a reaction. And because most reactions in nature, just give me a second. Yeah, so most reactions in nature are irreversible. The ones that we deal with are reversible and they're not many. However, we need to keep in mind a few things. There are open systems and closed systems, and also homogeneous solutions and heterogeneous solutions. So open systems is one way the vessel in which the reaction takes place. So in an open system, vessel is open, or rather let's say vessel where reaction happens. Is open. And in a closed system, the vessel where reaction happens is closed. So in other words, by its knowledge, it's sealed and nothing escapes, right? So here what this means is stuff can escape. And what that means for closed systems is stuff cannot escape. And homogeneous solutions, that means, okay, let me write this. Let's erase these. So there are things called species in chemistry now, in chemical equilibrium. These things called species simply mean types of things, right? Types of things in a reaction. I like how I'm just saying things. Types of things in a reaction. And what these things are, they're basically, I guess, states of matter, so to speak. Musa?
Hi, Dad.
Hi. Who's writing on the on the Jamboard? Oh yes, this one. Hi Magdalene, how are you?
I'm okay, and how are you?
Good, thanks. We're recapping on yesterday's class.
Okay.
Did you manage to get Jamboard onto your phone?
Jump on, yep.
Yes.
No, if I don't download them, I don't know why.
Oh, okay. I see you've downloaded Autopilot. Is it like, did you add it to your calendar or what?
I think on my calendar because I still download.
Oh, okay. No, it's fine. I don't think Autopilot you download. But it's fine. If you can share with Musa how you did it. I don't know how you guys will communicate it, but if you can, just share with her how you did it. Yeah. Anyway, we'll continue. Ne? Musa, so these species are. Let's see. I'll just.
Popular Butisha.
Yeah.
The chemical equilibrium equal fella.
You can check. Du. Grade 11, chemical equilibrium, right? Equilibrium. Doesn't look like there is in grade 11. Let's see here. Chemical equilibrium. Yeah, I think it's just grade 12.
Oh, okay.
Yeah. So.
Oh, and what airborne issue.
No, don't worry. Because I was checking what's going on in the class because I had a ping. So there's your Jamboard. Alright, so okay, what I was talking about was species in a reaction, and species in a reaction simply mean the states of matter, so to speak, that either the reactants or products are in throughout the reversible reaction, right? So this is what species refers to. So if a solution or the so just give me a second. Sorry, where was I? Yes. So if something is said to have homogeneous solution, what that means is that between reactants and products, they are in the same phase of matter. So they could be either here, it could be, so I'll just put an X there and I'll put an X there here. And that refers to the states of matter, right? So the X refers to, so it could be solids, or it could be liquids, all of them. It could be gas, all of them. It could be aqueous. But Ranchi, I would like to think it's mostly, or it's oftentimes aqueous. But in other cases, you will find that between reactants and products, the phases of matter or the species are different. For example, if you burn carbon, you mixing the solid carbon with oxygen gas, and that gives you carbon dioxide gas, which is also a greenhouse gas. And this reaction is irreversible because when you burn the carbon solid, not only do you get the carbon dioxide gas, you also have ash. and that means you can't, and because you can't convert ash to back to coal, that means here this is heterogeneous. But in this case, this would be homogeneous. Because let's go back here. If something is solid and it changes to a different form, there is a change. But then again, in the context of heterogeneous and homogeneous, the species that we talk about are solids, liquids, gases, and aqueous solutions. So a lot of the time in chemical equilibrium, we get substances that mix, sometimes in gas form, some in aqueous form, but nonetheless, you get substances in one of three of those phases. Sometimes you will get substances that are solids and start out as solids, and after the reaction, they form other types of materials, right? They become other types of species, and lastly, there are conditions for chemical equilibrium that we spoke about, and that are at dynamic equilibrium, the forward and the reverse reactions do not stop. Oh. There's Jambo. Sorry about that. I didn't realize I didn't have it. Yeah. So in open systems, the vessel where the reaction happens, stuff cannot escape, so things cannot escape. And then in a closed system, the vessel where the reaction happens, things cannot escape. Then we have homogeneous, where reactants and products are the same species, so they could be liquid, gas, or aqueous, or even solid. And then we also have heterogeneous solutions, or where the reactants might be something else and then the products will be something else. And how we can see that in other chemicals, if we burn carbon, lagala, or coal, we burn it in air. Oxygen is the gas that helps that gets, oxygen is the gas that I guess is, it makes combustion to be possible. That's how I want to put it, yes. And then when you burn coal in air with oxygen, or with fire, and then it uses the oxygen to burn the coal, you get carbon dioxide, which is a gas. And because you went from solid plus gas to gas, the reaction, we say it's got heterogeneous species. But then if we have, in other cases, we have reversible reactions, which are sometimes the substances reacting would be in gas form, and they would give us products that are in gas form. Nevertheless, in this case, the pressure, concentration, and temperature are the variables that change from time to time. And because they change, then they also affect the direction in which the chemical reaction is favored. So sometimes you would change the concentration of this, and let's say for argument's sake, this reaction would be favored. So more of these would be created, and maybe you would decrease this and more of that would be created. Those are just examples at the top of my head, they're not reference to anything, but yeah, these are just examples that are not reference to anything. So some reactions would go from this direction because maybe you change something there, and others would go in that direction, maybe you change something there or there. But like I said, these are just examples at the top of my head, they're not really referenced to anything. And then lastly, there are specific conditions for chemical equilibrium. The first one is that when dynamic equilibrium is reached, the forward reaction and the reverse reactions continue, they don't stop without stopping. So that means, in other words, when this equation has reached equilibrium, when for every nitrogen molecule, 3 hydrogen molecules make 2 of that NH3 gas, that reaction as well as the NH3 gas becoming its original reactants, nitrogen and hydrogen gas. That reaction going forward and that reaction going backward do not stop at chemical equilibrium. Then we also don't see big changes or obvious changes meaning macroscopic. So in other words, we don't see things like a color changing or a volume changing, or sorry, we don't see things like a color changing or anything like that, or bubbling or anything that shows that there's a reaction. But that doesn't mean on a very small level, one way we can't see with the naked eye, something isn't happening. Just give me a second. Sorry about that. And then lastly, the reactants and the products never get used up. Oh, because I switched off the mic. Okay. So the reactants and the products never get used up. What does that mean?
I don't know ki network yaka or what, but jump what I want to.
Try again.
Kira aki sure ki network yaka or what, mara jump what I want to.
Is it showing now?
No.
Still. But my screen is sharing. Let me stop presenting and present again. What's showing now on your screen? What's showing now on your screen?
I think ki network yaka.
Oh, okay. Do you think your network is slow?
Oh, eri kitu then kitu ina Africa one.
Okay, try that. Thanks. Let's see if that helps. Okay. So yeah. No. I don't think I need to open a new slide. Yeah, so that's yesterday's conversation. So now we continue the conversation. Okay, so again, in chemical equilibrium, when there is a reversible reaction, so I'll just put there reactants, products. So in a closed system, the forward and the reverse reaction happen at the same time. Oh, I think I should open today's Jamboard. Let me just. Sorry, in fair couple of seconds, yeah, kibule today's Jamboard, because yeah, I noticed. Ugh. Yes, let me open that one. Okay, so these are the things just really keep it in mind, ne? Let me add you. Yo, I go add. Okay, so add. Musa, Magdalene, Masaku. Okay, that is not necessary. Yeah. Sorry, go romeletse link ya Jimboard here today, ne? So you'll see it. You are seeing this screen with chemical equilibrium, closed system, reactants, products, ne?
Yeah.
All right, so the first thing we should know about reversible reactions in a closed system. So, reversible, the reaction can go in the forward direction and in the back direction, in the reverse direction. So, what that means is that in that closed system, where there is a reversible reaction, the forward and the reverse reaction take place at the same time. So they are simultaneous. Ne? They are simultaneous. Then the original reactants and the products that form exist in the same reaction container. So these reactants and the products, they are all in the same container. Remember, it's a closed system, and in a closed system, there's nothing that leaves out, that gets out of the system. So in other words, if we have an Ellen Mayer flask like that, and we've got stuff that's reacting, if it's open, then things can get out, right? But if it's closed, if it's closed, if it's closed, then nothing leaves in here. So everything remains in here. Ne? So in a closed system, which is what we are considering, closed system, and the reactants and and products exist coexist. Yeah, reactants and products coexist. They exist what day. So they coexist. And then thirdly, the rate of the forward reaction gradually decreases. So the forward reaction rate decreases, and this is because the concentration of the reactants decrease as they are being used to make the product. So come on, someone. When we mix the reactions together, they get used up to form the products. How do I make a simple example? When you're cooking, you use some of that electricity to then prepare your food. So in other words, whatever it is that you had in electricity reduces in quantity, and that increases that which you are going to eat, the cooking of that which you're going to eat. Another way, I guess even with food, I mean, if you're taking flour from the from the bin that you store it in, and you are deciding today I'm gonna take a portion of that flour and bake a cake or biscuits or anything that's a baked good, really. And then obviously when you are taking the flour, the eggs, the whats, it takes those things from wherever you stored them, which they are the reactants, to be baked to make a product which is the cake or pastry or muffin, etc. So what that means is, as this reaction progresses, as this forward reaction happens, then the quantity of reactants decreases. But as that decreases, then this quantity of products must increase. So in other words, whatever you put inside the reaction exits at the end of the reaction as products, and whatever it is that you put inside the reaction decreases in size, in quantity. But as it decreases in quantity, then that which the reactants become after reacting increases in quantity. So as forward reaction decreases, or forward reaction happens, reactants decrease and products increase. And this happens until the forward reaction rate, so in other words, until how, like, the rate the forward reaction happens at, until that rate equals the rate of the reverse reaction. And what this means is how do I don't want to say how fast or how quick I want, but rate is like so in other words, how can I explain it? In other words, the how do I explain rate? I want to explain the word rate. What's it? Rate. Definition. Okay. So yeah. All right. So a rate is a measure or quantity or frequency typically measured against another quantity or measure. So in other words, we've got a quantity of reactants and it quantity is measured against another quantity of products, because and I guess it's also measured against how over time the reaction happens. So over time, as the reaction happens, yes, time is the correct quantity to compare with. So when I went during the reaction, as the forward reaction happens, then the rate at which the reactant as the forward reaction happens, then the rate at which the products are formed increases as the rate at which the reactants the rate at which the reactants react to form the product. Yes. And then what's this? And then again, as that same forward reaction happens, so here we'll say, so this is the forward reaction. And then the reverse reaction. So the rate of the reverse reaction gradually increases as the forward reaction happens. So in other words, when we continue having the forward reaction, the reactants, when they decrease and the products increase, that's when the reverse reaction gradually happens. Gradually happens. Is Magdalene back in? Okay, I guess that's everyone, yeah. Magdalene?
Yeah.
Is Jamboard showing now?
Yeah, bo.
Alright. Sorry?
System ibigay with like a break ne.
Sorry?
Chemical equilibrium. Fiona.
Yes, it's the one showing. If you have the screen open, it's the one showing on your screen.
Huh?
If Uji, how are you accessing the class? Are you accessing only on the video, yeah, Google Meet?
Yeah, bo.
Oh, okay. So then you should see a split screen. To the left, there's Jamboard. Sorry, there's a textbook, and to the right there's Jamboard.
Yeah, Kion.
Okay. Yeah, so as the forward reaction happens and the reactants decrease, the products increase, which means the reverse reaction gradually increases or takes place. Gradually takes place or happens. Yeah, I was using the correct English words. And as it increases, the concentration of products increase. So products increase, but reactants decrease. Ne? So as this decreases, this increases. So something's gotta give. Something goes down in number, then the other one has to increase in number. And once the concentrations of the reactants decrease and they get to a certain point, and the concentrations of the products also increases and it reaches a certain point. So there, at that point, there is a point where those two coincide, and at that point, the rate at which the reactants form the product is the same as the rate at which the products form the reactants. So in other words, the forward reaction rate is the same as the reverse reaction rate. All right, so okay, so far we're still together, ne? I just want to see if Nobush is gonna join us soon. All right. Okay, let's continue. Let's continue. So, all right, things that affect chemical equilibrium position. So things that affect chemical equilibrium. Things that affect the chemical equilibrium. These include temperature, concentration, and pressure. Ne? And this is because, remember, we're dealing with open and closed systems. Ne? And some reactions are exothermic, some are endothermic. Exothermic meaning they produce or give off energy. Endothermic meaning they require some energy to react. So temperature, so depending on the type of reaction, sorry about that. Depending on the type of reaction, if the temperature is either increased or decreased, then the equilibrium can shift, right? So a rise or increase or decrease of temperature can affect equilibrium. So increase or decrease of temperature can shift the balance temperature. And then concentration, increasing the concentration of one or more of the substances in the reaction. So changing the concentration of substances in the reaction. This could be either by decreasing, increasing either of the reactants or products, and then an increase or decrease in pressure. So remember, closed systems, nothing leaves the vessel. And because nothing leaves the vessel, that means you could probably press on the space where the chemicals are reacting. And if you press on it, you decrease the volume. So that means you increase the pressure. So that will have a different effect on this will have an effect on the chemical equilibrium and shift its balance or position. Then there is something called Le Chatelet. What? How do you pronounce it? Okay, so Le Chatelet's principle. Hi, Nobuhle. Is she in yet? No. Turn down screen. Hey, Nobuhle.
Hello.
How's it going?
Well, thanks. How are you?
I am doing my best.
Good. That's good enough.
Yeah, it's been a day. Let's just wait for the others to show up. So today we're doing chemical equilibrium, ne, with the girls.
Yeah.
I'll be sure. As in, there's so many things I need to back up. Did you receive the link to yesterday's Jamboard?
Yes.
Alright. How do you find self-study based on those notes? I wanna know.
I didn't study yesterday.
Yeah, it's not necessarily yesterday per se, but like if you have to refer to yes.
Yeah, it's easy for me if I had followed in the lesson and then I'm doing revision.
Oh, okay. Yeah, I guess then the video would definitely help. Yeah.
Yeah.
I made the recording. It's just uploading is such a schlep. It takes so much time on this end. Okay, I sent Musa an invite. I hope she received it. Hi, Magdalene. Welcome again.
Thank you.
Yeah, I need to really yeah, but this situation is gonna be fixed. It's already fixed. All right. Let me hide this. Alrighty, so I'll have Jamboard. I'm not sure, ne? No, okay. So yesterday's notes were these, but fortunately then we have a video, ne? It's just 7 slides, but we started off defining some of the key concepts that have to do with atoms and molecules. Why is that important? Because we need to be able to visualize them, the atoms in molecules and as individuals, and isotopes. And then we did an example, but this one is explained in the video there, where we look at isotopes. So you know how stuff is radioactive, right? Like uranium is radioactive and hello. Okay, I'll just speak. I guess you listening. So Nobisha was saying, you know how stuff is radioactive? That's because yes. Cool. I'll just continue. So how stuff is radioactive? It's usually because the number of neutrons increases, but the number of protons doesn't change. So when that happens, we have what we call an isotope. And that's just a variation of the same atom with just a different number of neutrons. Neutrons being the non-charged things at the center or at the heart of the atom. Then we did an example with that, which kind of makes us come up with the number for the relative atomic mass units. And this is relative to the fact that normally occurring chlorine is 75% of all the chlorine in the world. And isotope 37 of chlorine is only 25%. So relative to those numbers, we had to work out what the relative atomic mass is, and then we found it. We then went into touching a little bit on the conversation here chemical equilibrium, right? So when things react, something always forms at the end. Like if you burn coal, you get carbon dioxide and something else. So how we make sense of these reactions, we need to check for what the atoms in the reaction are. Where is it on the periodic table? What is its atomic mass units, electronegativity, atomic number? Those information that data gives us important information about the atom itself, but not only for the atom, but also for the molecule in which the atom finds itself. Because when we know what a molecule is made up of in terms of the atoms, how many are bonded and how are they going to react, then we can sort of make sense of the reaction and sort of balance it, right? And when we balance the reaction, then we can work out the concentration, the number of moles, and the volume. So for now, number of moles, don't worry too much, but that has to do with sure. Moles is like a set quantity, and in that quantity you can fit, I think, to Avogadro's number, like 6.024 times 10 to the something of atoms in that set space. So from that, the concept of mole comes, I think. But yeah. We then talked about open and closed systems. So in some reactions, or in a lot of reactions, things could happen in a closed system or in an open system. Now, when a reaction happens in a closed system, it simply means there isn't anything that can leave. And when it happens in an open system, there's stuff that can leave the system. And then secondly, we've got homogeneous solutions and heterogeneous solutions that are a result of mixing products and reactants that form products and then back again. So with homogeneous solutions, the reactants and the products, they're in the same phase of matter, state of matter, or we call them the same species. But if the solutions are heterogeneous, then some might be solids, some might be liquids, some might be gas on either side of the reaction. For example, if we have an irreversible heterogeneous reaction in an open system where we burn coal as as a chemical element called carbon, where we burn it in solid form in the presence of oxygen, which is gas form, we produce smoke, which is usually carbon dioxide gas. So the system's open, the carbon dioxide escapes and it goes into the ozone. Unless if you think then the ozone layer is a closed system, is this part that closes the system. But yeah, if it were in a lab and the gas escapes, we'd say it's in an open system. Then we have a reversible reaction where two gas types react and they give us another gas. So here we say this is homogeneous because everything is a gas. And lastly, with chemical equilibrium, when equilibrium is reached, the reaction that goes forward is the same, and the reaction that goes backward don't stop, they keep going on. And then there aren't visible changes that we can see with our eye, but on a microscopic level where we can't see with our naked eye, something's always happening. And lastly, the reactants and products never get used up. So in other words, because the reactions are reversible, whatever reacts to form the product, as it decreases in quantity, and this increases in quantity, the products increase in quantity, then the products can also react to form the products again, thus continuing the loop from reactants to products and products to reactants, reactants to products, products to reactants, and reactants to products and products to reactants. The difference is between these two is that this one is reversible, so it can go in circles like that, but the one before, the one above, is not reversible, so it's only one directional. You cannot burn coal in the presence of oxygen and carbon dioxide gas, and the carbon dioxide gas gives you back the solid and the oxygen. What generally happens is you get ash, and because you get ash, you can't turn ash back into coal. So yeah, that's the long and short of chemical equilibrium. But please, Ngela, like don't sweat the definitions just yet. We're gonna ease into this content. Né? We're gonna go step by step by step by step. Alright. So what we just talked about now, Nobutle, before you came in, was from the summary I just gave you. What happens in chemical equilibrium problems that we solve in our classes, né? And they usually involve reactants and products that are in a closed system. So if you want to think about a closed system, you can imagine it like if, let's say, a reaction is happening in an Erlenmeyer flask, right? A reaction is happening in an Erlenmeyer flask. And as it happens, that Erlenmeyer flask is closed. It's propped up at the top so nothing can leave or come in during the reaction. So it's a closed system. So this is a closed system. Now in that system, the forward and reverse reactions, this symbol shows us a reaction. So the reaction of reactant plus reactant forming products, as well as the reaction of products reacting to form the original reactants. These reactions happen at the same time. So as soon as reactants react to form products, as soon as these decrease in quantity to start forming these, you also start having these decrease in number and forming these. So because the reaction happens at such a microscopic level, these reactions happen so quick that they happen quite quick. Then reactants and products can coexist. So in other words, whatever you have as the reactant and as a product, they coexist. So it means you will have reactants forming products and products forming reactants at the same time. And again, as the forward reaction happens, the reactants decrease, but the products increase. And again, as the reverse reaction gradually takes place, it should be the products decrease and the reactants increase. Yes, I think I swapped the wording there. It should be reactants increase, products decrease, I believe. All right, and then and then this happens until dynamic equilibrium is reached, and this continues on and on and on until maybe you open this and you spill everything out so that you can clean your lab equipment. And there are only three things that affect chemical equilibrium. They are temperature, concentration, and pressure. Temperature, because in some reactions, when we increase the temperature, we might affect which one gets produced more. Is it the product or is it the reaction or reactants, or which one's production is limited when we increase or decrease the temperature? Is it the reactants or is it the product? And then also with concentration, if we change the concentration, so in other words, think about like oros, and I like oros because it's concentrate. um, when you have, like, let's say you're mixing oros, 1 part oros to 4 parts water, then if you increase the concentration of the oros, let's say you make it 2 cups oros, 2 cups water, will the oros be same flavor as the recommended dose, or will it be more sweet? It'll be more sweet. So that means the reaction is in favor of the concentrate because you increase the amount of concentrate. So similarly with chemical equilibrium, we think of it like that. If we increase the concentration of something, then something else could be formed. But because the reaction, when we increase the concentration, is in favor of, because, yeah, it will be in favor, because as we increase the concentration of something, one of the reactions, either the forward or the reverse, would be favored by an increase in concentration of either reactant or product. And then lastly, pressure. So because these chemical reactions happen in a closed container, then what that means is if we shrink the container and we increase the pressure, then something else might happen to the things reacting in the chemical reaction. So it could be the volume of the concentration of something changes, or the number of moles of one of the two, the reactants or products. And then, yeah, so we're gonna discuss what's called Le Chatelier's principle. And Le Chatelier's principle, it focuses on closed systems. So Le Chatelier, and this it's important to be familiar with it. It's very important because it's used in almost all the reasoning in chemical equilibrium problems in matric. Right, so it speaks also to closed systems. It's applied mostly in closed systems. And these closed systems must be in a dynamic equilibrium state. So reaction must be in a dynamic equilibrium state. And we need to keep in mind also that temperature, concentration, and pressure do affect the balance of the equilibrium position. Right, so there's different ways to apply this rule, and they apply to changing either the temperature, the concentration, or the pressure. Right, so should we have a change in temperature or change in concentration or change in pressure? There's a way to discuss these changes, Le Chatelier. So we're gonna start with the ones with how to articulate Le Chatelier's principle in solving chemical equilibrium problems, and then we're gonna get into the steps. So it's a lot of theory, but it's necessary theory. And some of the things that are going to show up going forward, I'll just refer to like things like you see here there's a delta H is less than 0. This just explains that the reaction is exothermic, so it gives off energy. So that means it's what do they call, what's this word, enthalpy. And we'll explain all those concepts, but for now we just need to understand that Le Chatelier's principle applies to changes in chemical equilibrium conditions. And we'll start first with temperature, right? Change in temperature. So if we increase the temperature, let's say there's an increase in temperature, right? So temperature, we'll just write there degrees Celsius. And we're going to contrast that with a decrease in temperature. So we're going to look at those two and then apply the Chatelier's principle to both. So when we have an increase in temperature, so in other words, the reaction system is heated up, right? So there's external heating, and if we decrease the temperature, that means we are cooling the system down. Then when the temperature is increased, the reaction that decreases the temperature of the system, so the reaction that absorbs heat, right? So reaction that absorbs heat. So I hope we're still together, because like I said, it's a lot of theory, but it's necessary theory. And please stop me if I'm going fast, ne? And just ask. And if there's anything that's not clear, just give me a shout and say, hey, something's not clear, where does it come from? Then I can seek ways to go back to it. Oh, I must then switch the next Jamboard slide like that. Yeah, so when the system is heated up, the reaction that absorbs heat is favored. And this is usually the endothermic reaction, right? So endothermic absorbs heat.
Also,
Yeah.
can you break down endo and thermic?
All right. Let me do that. You know what? I think I'll have to break down a lot of the other concepts like that. Oh no, because yesterday we did talk about heterogeneous and homogeneous, describing the differences between hetero and homo, and also what was the other thing? The prefixes, oh yeah, the suffixes of neutron, proton. I think we talked a bit about that. And then also reversible, irreversible. Oh, macro and microscopic. Yes, we did talk about those two differences. Yes. All right. So the question is to break down endo and exothermic. I like that question. So endothermic and exothermic. You ever watch like things? I don't know if there's mention of this in science fiction, but you ever seen in the movie Avatar with the blue aliens from a planet called Pandora?
Yeah, it's 3 hours long.
Yes, James Cameron is like that. But the cool thing about there's these robots that who's that guy died in Quadrich. Remember that villainous soldier who had beef with Jake Sully because Jake Sully defected and joined the native aliens.
Yes,
Yeah, so he wears a suit. So he wears a suit and he just gets inside it, but it amplifies his human gesture. So if he walks, it amplifies the movement because it's larger, it's bigger. So something like that would be an exoskeleton. So it's like a skeleton, but that's outside. We can even bring it closer to Earth. Insects don't have a skeleton on the inside, they have an exoskeleton, which is their shell.
yeah.
So the prefix exo, let me just use this. So the prefix exo means outside. And then speaking about skeletons again, humans, mammals, reptiles, a lot of reptiles tend to have their fish as well, tend to have their skeleton inside of their bodies. So our skeleton is inside of our bodies, it's embedded deep within muscle. So we say that it's an endoskeleton. Endoskeleton. Also, there's endocrine and exocrine glands. Endocrine glands being glands in the human body that secrete whatever it is that they secrete, but from inside the human body. Whereas exocrine glands would be part of the human body, but excretes stuff from the body from outside the human body. And examples of exocrine glands include, I believe, your ceruminous glands in your ear that make the earwax or cerumen, and also I think the sweat glands on your skin, inside your skin, which produce or eliminate sweat. And then lastly, the suffix thermic, or rather therm, therm refers to hot or cold. So in other words, anything that has to do with temperature or sensations of heat and cold. And then the IC part just tells us having to do with that. Yes. So exothermic means taking heat outside, and endothermic means taking heat inside. And yes, to identify these in equilibrium, when a reaction has delta H less than 0, then this means it is exothermic.
Like, for example, if ammonia is released into the atmosphere and it mixes with oxygen,
Okay.
will that be an isothermic reaction?
It depends. Like, I haven't seen the reaction myself, but let's say the reaction happens, right? Let's say it happens in a vessel. Maybe you put it in a flask, and then as the reaction is happening, then you put a thermometer next to the Erlenmeyer flask and you find that the temperature increases. Then in that case, that reaction is exothermic. Yes. Think about like the heating up of your cell phone's battery. So in the battery, the lithium polymer ions are doing the thing, moving charges around and stuff. But if that battery heats up, then it means there's a reaction going on there. And that reaction is exothermic. You can tell it's exothermic because there's heat being released.
Yeah.
That's the long and short of it. Yeah. So then the reverse would be endothermic. The reverse would be endothermic, right? Now this symbol here is called enthalpy. Enthalpy. We can look at its definition. Enthalpy definition. So enthalpy is like a thermodynamic quantity equivalent to the total heat content of a system. It is equal to the internal energy of the system plus the product of pressure and volume. So that enthalpy, if it's negative, then it means the reaction is exothermic. Right, so basically if you want to visualize it in graph form, to the left of the screen, here's what enthalpy is. You have reactants giving products, and there's a certain energy that the reactants are at when they combine, right? And when they react over time, the energy increases. And as the energy increases, then the heat is released. And that also happens as the heat's released, the products form, but they result at a lower energy level than the reactants originally. So the reactants start out at a high energy level, they give off heat, and as that heat's given off, the reaction forms products. But at the end of the reaction, the products have got a lower energy state than the original reactants. And in a different scenario, when the reactants are at a lower energy level and you introduce heat, then that heat allows for the reaction to progress. And when that reaction progresses, then you find products that because the reactants have absorbed heat to form the products, then the products are formed at a later energy state. And so like in our definition, then this would be, we have an energy state here, and we have our reactants, and in our reactants, the energy level is low, the enthalpy is positive, and that's because the energy of the system has to be increased to such a point where the products form because heat has been reactants, yes, because energy has been introduced to the system. And here, when there is a sorry sorry, back to the discussion, Yale Chatelier, when the temperature changes and the temperature is decreased or the system is cooled, then the reaction that is favored is the one that releases heat. So favored reaction is the one that releases heat. Reaction that releases heat. And in other words, this is the exothermic reaction. Yeah, that's the exothermic reaction. And what happens is the reactants start out at a high energy level, and then energy is given off in the reaction. So the reactants are at a high energy level, then they react to form products whose energy level is way below that of the reactants. And that simply tells us that the enthalpy decreases because so here this would be exothermic, and here the enthalpy increases, yes. So with an exothermic reaction, the enthalpy is less than 0 or it's negative, and that would simply mean that the reaction is exothermic. And in the case where the change in temperature is a drop or there's a cooling in the system, then the exothermic reaction would be favored. So in other words, within the reaction, that which has the fact that there's a lower temperature or lower energy, then the reaction that favors the release of heat, because the reaction would want to give off heat because the conditions around it are cool enough. So it would want to give off heat. Also because the things in the reaction are not gonna end, because with closed systems and the substances that are in the reaction, they always react and react